Today, we're gonna start discussing metallurgy. Our class is taking a big detour now. The first part of the class so far was essentially learning a dictionary. By now, if I say MIG or TIG, it sounds like second nature to you, but for many of you, just merely a month ago, that meant nothing. And if we talk about the toe of the weld or the face of the weld or so many of those things now are part of our language. And we needed to learn those. What we did so far is learning this dictionary. But I tried to bring in as much science as I could and as much practical meaning as I could as we were discussing that. But essentially, it was learning a dictionary. I have a question that is, if quiz 2 covers from the beginning? And the answer is yes. It's not that I'm going to go back and ask questions just to make sure you don't forget. It's in quiz 2 and quiz 3 and all the 5 quizzes, we're going to be building on knowledge. So you can never forget what MIG and TIG is, or what a root pass is, or a hot pass is. You can't. And if you start forgetting it, you need to go back and review it. That's because it's our language, not because I want you to memorize a lot of crazy things, but it's the language we need to speak. Now, and into the future, I'm going to discuss some basic metallurgy. This is not a class on metallurgy, but we cannot talk about welding without discussing the most basic aspects of metallurgy. And that's what we're going to do over the next 3 lectures. And again, you cannot forget it. So I'm not going to come back to make sure you didn't forget it, but I'm going to be using this knowledge because it's part of our language that we're building. And this class is like climbing stairs. And then you might look back and say, oh, we're up in a tall building, but we did only one step at a time. So about metallurgy, which is going to be brief, we have been dropping little hints here and there. For example, we already said that if I cool down faster, I'm going to end up with a harder weld than if I cool down slower. We already said that, but I didn't give you much of a foundation for that. For some of you who have a background in material science, it's kind of self-evident because that's part of your education that you already have. For some others of you, for example, mechanical engineers like I was like, oh, really? Tell me more about it. So in the next 3 lectures, we're going to essentially have a crash course on metallurgy. I'm going to bring into the class pretty much everything that is important. There are many subtleties which we'll not get into, but you'll be conversant on metallurgy. And I picked to start carbon steel. There are 2 reasons for this. Number 1, pretty much everything you weld is steel, right? Of course, there are people who weld titanium, there are people who weld aluminum, but in the end, most of the weld we end up doing is in steel. So let's make sure we address what we do the most. In addition, steel has very interesting properties as it's welded. So if we learn steel, the rest of things will be either a modification of what we learned for steel or even easy. And the third thing is that we know so much for steel. There are many things. We have formulas which we'll teach you today in the seminar. There's so much we know about steel that we can make predictions. The welding of steel is close to being an engineering. The welding of other materials is still a mixture of science and alchemy. Science when we can go deep enough, but still cannot have general formulations. Sometimes it's alchemy because we start trying crazy things until something works, but not the case of steel. So let me start with an introduction. I'm a mechanical engineer. I got my PhD in material science, but I'm still a mechanical engineer. Alejandro, your TA, that's a true metallurgist. So I'm going to dedicate the next slide to Alejandro, which is the definition of a metallurgist. I got this definition from my predecessor here at the university through one of his students. And I cannot find who wrote this quote, but whoever wrote it is an awesome person who probably doesn't have many metallurgist friends left. But it's have a joke, but the other half has some truth. And it says, metallurgist is a pseudoscientist who uses undetermined suppositions, indefinite theories, and inexpressible hypotheses, which are based on reliable information and certain quantities and incomplete data, and keeps going. And the last words are perhaps especially interesting. If you talk to a metallurgist, you'll be very hard pressed to get a straight answer from them. They end up always saying, it depends. And it's true, most things are answered as it depends. But sometimes it always depends on the same thing and you get the same straight answer. Metallurgists are harder to pin down. It's like politicians. So this thing that is written here is a little bit of a joke, but a little bit true in that a material is made out of billions and billions of atoms. So whatever we know about a material, we have to know it at a macro level, at some sort of average level. And not only is billions and billions of atoms, but the atoms form grains and microstructures. So pretty much everything we say in materials has somehow a counterexample somewhere, right? It's not as clear cut as mechanical engineering, in which a spring is a spring and it's a spring. Metals are much more difficult. So it's very easy to laugh at metallurgists and their lack of precision and their ambiguity. On the other hand, if we didn't have metallurgists, we would have no bridges, no airplanes, and no cars. Actually, we would live in the Stone Age if we didn't have metallurgists. So let's start by acknowledging we're treading into a new territory in which ambiguity and poor accuracy are pretty common, and still we accept them and we get very, very, very important results from that. So I want to start with talking about metallurgy with something that sometimes is a common misconception. As a mechanical engineer, I was taught that 4140 steel would have so many megapascals of strength. And it's in books and things like those. But that is not true. That is not true. It's true sometimes and sometimes not, right? It depends. And that's what drives people like mechanical engineer crazy. Because a material, when we define something like 4140 or something, or we give it whatever name we give, a P1, whatever it might be, that material has a certain chemistry. But the chemistry is only the good beginning. A chemistry is like defining a book by saying it's made out of sheets of paper. But what is written on that book is gonna be very different one book from the other. And in a metal, even if you have the same composition, you can have different microstructures. And this microstructure is gonna give you the properties. So let's start. For some of us in materials, this is self-evident. For some others, this is kind of a big revelation to say, this steel with this name does not have a defined property. It depends whether it's quench and temper, whether it's like annealed, whether it's so many other things you can do. And because in welding, some parts are hot and some parts are cold, and some welding procedures are hot for long and some other welding procedures cool down fast. The same material with the same first and last name is going to have very different behavior. And that's where we are going. So the fact that we can name a material doesn't mean that we know the properties. We have to know the microstructure. Very, very important. What the material looks in the microstructure. So what are the levels of microstructure? Well, let's start with an atom. I'm not going to go any finer than an atom, but I think an atom is fine enough for our purposes, right? In the end, we're welding bridges. Now, the atoms, for those things of God, and it is that way, and we have to accept it. If you put a bunch of atoms, they don't scramble randomly. They organize themselves. If you want, you can call it self-assembly, right? Like it sounds very, very high tech. But that's what happens. You put a bunch of atoms and they themselves decide how they're going to arrange, right? And that's what is called the crystalline structure, the crystal cell. For example, here we have something that is called BCC. And I believe all of you, MatE and pretty much everybody else, went through an introduction to material science. Now, these multiple cells, these multiple local groups, right? They create a grain, right? And here we have a structure of what would look in this drawing. That is what you see in a microscope of a metal. Inside each of these polygons, everything is arranged, whether it's BCC or FCC or whatever it is, but the atoms are arranged in a particular crystalline structure. To some extent, the crystalline structures are like streets and avenues, because you get to see in this crystalline structure how they depending on the angle you look at them, they might look all lined up. And in each grain, all the atoms are lined up in the same direction, but different grains can have the atoms lined up in different directions. So this is a little bit like a map of an old city. Like Buenos Aires, my city, or Paris, or your favorite big city, not a new city like Edmonton. In the old cities, people in each neighborhood, they made the streets parallel and perpendicular and straight. But when two neighborhoods come next to each other, then the avenues and the streets don't add up. And you get to see areas in which the streets and avenues are kind of all odd because they're at the edge of neighborhoods. That is exactly what a grain boundary is. The atoms are coming in a straight line for one of these grains, and in a straight lines for the other of those grains. But those straight lines don't match up. And this lack of matching is what we call the grain boundary. And it has properties, because when an atom is in its crystalline structure, it managed to reduce its energy to close to the minimum level it can have. But when an atom is in a grain boundary, it doesn't know if it belongs to one crystalline structure or the other crystalline structure. It cannot give away all its energy. So it's at a state of somewhat higher energy. And when atoms have somewhat higher energy, then this energy can be used for things, can go from corrosion to mechanical properties. Now, we went from one atom, and a bunch of atoms gives us a crystalline cell, a bunch of crystals, right? And even if the material is the same in chemistry, what this arrangement of atoms, whether they arrange it like FCC or BCC or whatever it might be, and whether we have big grains or small grains or elongated grains, all that is going to change very much the response of our material. And that's quite amazing. We call it the same name. We can call it 4140, but I can give you pretty much any property we want on that material. We cannot assign a property just to the material name. So let's talk about steel. And before we talk about steel, I want to talk about pure iron. So we have here what is called the iron-carbon phase diagram. All of you have seen it before, but for some of you, it's old news. For some of you might be like might trigger some traumatic memories, right? But this is a map. This is just a map. In the horizontal axis, we have 0 means 0% carbon, which means 100% iron, pure iron. And as we move to right means I add more carbon and more carbon and more carbon as an alloying element. And right now, I'm not adding any other alloying element, just iron and carbon. And by the way, let me tell you, this is so useful, but that nobody does that for a number of good reasons. Nobody has only iron and carbon. But this diagram represents most steels that are welded. So if we look on the left where it says 0 in the horizontal axis, that's pure iron. Let's look at the vertical axis. It says temperature. And these different parts of the map, these different countries in the map would be the different ways in which the crystalline lattice can be arranged. So let's look at only iron right now, pure iron. So we have this red line that says from room temperature up to 911.5. I don't know, it says percent, but that is wrong. That's degrees C. From room temperature 0 Kelvin to 900 degrees, give or take, the iron, by the grace of God, has the atoms arranged in this BCC structure that has a bunch of properties that are very well understood. Among other things, these properties that the material is strong and difficult to deform. Now, at 911.5 degrees C in pure iron, and more or less that for normal steels, something happens. And for those things of the laws of thermodynamics, now, at those higher temperatures, the atoms of iron say, you know what? This BCC type of structure, which we call ferrite, they don't like it anymore. They say, we want to arrange ourselves in a different way. And it's called an FCC way. And we call that phase austenite. And austenite, that has that different way of being arranged, has properties too. Among those properties, that is easy to deform. So now let me, just having explained only this to you, let me tell you something that is quite amazing. Let's not talk about welding, let's talk about forging, where you have like a, I don't know if you watch on TV, there are shows, right? And there are clubs of forging. You get your iron red hot and you start banging it with a hammer. Of course, the hotter, the softer. That applies to everything. But in iron, there is something in particular that if it is hotter than these 911.5 degrees, then the atoms went from being arranged like ferrite, which is BCC, they rearranged themselves as austenite, which is FCC. And if you study the crystallographic structure, it's a lot easier to deform. Super important in iron to be in the above this austenite grain where the deformation is easy. Very interesting. Very interesting too that sometimes nobody cares and sometimes it's essential. If you keep heating up pure iron, for those things of thermodynamics again, goes back to its original arrangement of ferrite. And people gave names at the beginning to this. They called, this alpha ferrite. Austenite is called gamma. And then when it goes back to ferrite, they call it delta. But let me tell you something, ferrite is ferrite. Whether it's alpha or delta is the same thing. And for those of you fluent in Greek, you might have noticed that I skipped the beta. And beta, what happens is, was related to magnetic properties. And you could see when you do these experiments to see phase changes, you see something happening that people attributed to a phase change. But it's due to magnetism, and that was what is called the beta iron. Right now, people recognize that there is a magnetic transition, but nobody sees it as a phase transformation. So we don't have beta anymore. We have alpha, skip beta, gamma, and delta. Something interesting about iron and steel is such an old discipline that things have names similar to minerals, right? So the alpha iron, we call it ferrite, has a name, and then austenite. And then I'm gonna be dropping other like cool alchemist sounding names for steels. Modern materials such as aluminum, no, they don't have any funny name. Aluminum is aluminum, and and nobody has like old mineralogic names for it. So this is the effect of temperature on iron. Let's look at this, the effect of carbon. Let's look at this austenite region, okay? That is marked in green. For pure iron, 911.5 to 1396 degrees C, we are in austenite, gamma iron, with 0 carbon. But if I add carbon, carbon is what is called an austenite stabilizer. Look at this. If I add carbon, now it says that at this, the temperature at which I would have austenite, it can be lower and can be higher, right? So austenite is going to be austenite even colder than before because I have carbon that stabilizes it, and hotter than before because I have carbon that stabilizes it too. So all this area indicates I have a mixture of iron with carbon in solution, and that's all I have. When I cross the line, this is a single phase. When I cross the line, I get into a two-phase region. And here where it says alpha and gamma, right? That's not a minus, this is alpha and gamma. And what this says is that if I'm in this little triangle here, using the Gibbs phase rule, which I'm not going to go over in this class, but you saw in quite detail in MatE 202, it says, now we have an extra degree of freedom. So in here we have a mixture of ferrite and austenite. This part is what we call the intercritical region. And depending on the temperature we would have here, at this temperature over this line, we would have 100% austenite. And over this other line down here, we will have 100% ferrite. And let me tell you what happens on this line in a minute. So all austenite, that is iron with carbon in solution, and it has an FCC structure. Here, this so thin that we cannot tell it from the red line, is ferrite, that is BCC iron with a little bit of carbon in solution, almost nothing. Carbon is pretty much insoluble in ferrite, very little. Here, at this temperature, we can have it. This map also has some other interesting points. Imagine I have, let's say, austenite, and I put too much carbon in my austenite. So I have iron with carbon and iron with more carbon at this temperature and iron with more carbon. But if I have too much, some of the carbon cannot be dissolved. And we understand this. If you like to have, if you make lemonade and you put sugar, the sugar dissolves in the lemonade. And you put another spoonful of sugar and it dissolves in the lemonade. But there is a point, and depending on how much of a sweet tooth you have, it gets to a point in which if you put much more sugar, the sugar will not dissolve because you reach what is called the solubility limit, and the sugar stops dissolving in the tea and falls to the bottom. It stops dissolving in the lemonade and falls to the bottom, right? And the same happens here. If you put too much carbon, it gets to a point in which you cannot dissolve any more carbon and comes out. And the way it comes out in steels is not as just graphite. In cast irons, yes, but not in steels. It comes in the form of this very odd looking crystal structure that is stoichiometrically Fe3C, that is cementite, right? It's some sort of a soft carbide, right? This is, but has doesn't have easy slip planes for the formation. So this is quite a hard and brittle material, this cementite that precipitates. So I don't need just to put too much carbon. I can have a constant amount of carbon, for example, 1%, and as I cool down, I'm in this single phase of iron with carbon in solution. When I cross this line during cooling, guess what happens? My solubility limit has changed, and now I precipitate this cementite. There is one especially interesting point. There is this one called the eutectoid point, because if I were to have this composition that is 0.77% carbon, and this is the composition, for example, of train wheels or railroad tracks. This is more or less this composition. We keep cooling down, and we're in the single phase of austenite. And when we cross it, all of a sudden, what we have is ferrite that can take very, very little carbon, and we have cementite. And those two are mixed. What comes out of here has one of these mineralogic names called perlite. So here I put some photos, and they are not all the photos of the same steel, but they are photos that are representative. Let's talk about a steel that has 0.2% carbon. That is a very common amount of carbon in structural steel and pretty much everything that is very weldable, about 0.2% carbon. Sounds like very low, but to give you an idea, 0.4% carbon is high. And more than 0.4% carbon is really high. And 0.77% carbon is crazy high, right? That you don't make many structural elements at pyritic composition. So let's use our iron carbon phase diagram. I made this vertical line that corresponds to 0.2% carbon. So a given steel will live on this line. It can be hotter, it moves up, can be colder, moves down, but the steel is on this railroad track and is 0.2% carbon. Let's say we're in 0.1. That means we have this steel that is at 1050 degrees there. How does it look like, a steel that is at this temperature? Has anybody seen steel at 1000 degrees? I'd like to see in the chat if anybody tells me how does this steel look like when it's at 1100 degrees or 1000 degrees. Yeah. It's bright orange. It's a bright orange, starting to verge into white, and of course it's malleable. It's beyond orange. It's a very, very bright orange, very bright yellow, right? That's what it looks like, but it's still solid. And if we were to look at it in the microscope, and some people can do this thing called hot stage microscopy, but here I put a representative image. This is what the austenite grains look like. They look like these polygonal things and without too many interesting features. If you remember, when I start to describe atoms, crystal structures, and grains, it looked like that. That's like some sort of a tiling without too many interesting features. Now, if we are in 0.2, in which we are, say, at about 800 degrees, right? Now it's red hot, right? It's quite red orangey. So we're looking at something that is glowing red. And in this case, we have a mixture of austenite and ferrite. So you see these austenite grain sizes, that the austenite grain boundaries we have here. The ferrite starts to grow on the austenite grain boundaries. And if you do the if you get deeper into the metallurgy, you'd say, why does the ferrite appear in the austenite grain boundaries? That relates to this issue I mentioned, that at the grain boundary, the atoms don't really know what side to what grain they belong, and they have a relatively higher energy. So when it's time to transform, the first things that transform are the things that have this high energy that are in the grain boundaries. So this microstructure is quite complex, but what I want to draw your attention here is how we have the ferrite, and this marks the boundaries, the grain boundaries of what used to be austenite. And this is what is called primary ferrite, because we are having austenite, and as we cool down, ferrite appears. We call that primary ferrite. And then let's talk about point 3. And in point 3, what happens is we had some amount of primary ferrite, and this is a different steel, but the concept is the same. You see these white things, these white features here? Those are the ferrite grains. Those are the primary ferrite. Now, what used to be austenite, I have this austenite, some of the austenite transforms into ferrite, and when I reach this temperature, right, which is called the A1 is what the name people use for this. There is a temperature below which you can have no austenite at any composition. So when I'm right before crossing this line, I have ferrite at this composition and austenite. And I can use the lever rule and see, I have so much austenite, so much ferrite. But as soon as I cross this line, the austenite is unsustainable. And what we get is this mixture of ferrite and cementite that is that grow in a lamellar structure. Is called a eutectoid, and the traditional name for steel metallurgist is perlite, and looks like this fingerprint you see here. So in this microstructure I'm showing you here, we have two things. We have the primary ferrite that came when austenite first started to decompose, and then we have this perlite that is what came out when the austenite, the remaining austenite transformed into ferrite and cementite together. This is the look of perlite. The white here is ferrite lamella, like sheets of ferrite. And the black lines, those are sheets of cementite. So we have ferrite, cementite, ferrite, cementite, ferrite, cementite, like that. You can imagine perlite is fairly strong, right? It's kind of a composite material. Actually, it's exactly a composite material, right? Very interesting. My hope is in this slide, you start to see how you can see a structure develop. How many microstructures we have here? We have two. We have primary ferrite and perlite. Two microstructures. How many faces we have here? Have two faces. But let's pay attention very well to what these faces are. One face is ferrite. The other face is cementite. Perlite is made of cementite and ferrite together, this lamella. So this white we see here that I'm pointing with my marker is the same white that we see anywhere in here. That is BCC iron, ferrite. And the black is this carbide, this Fe3C cementite. All right. So we talked about the effects of temperature, and we talked about the effects of carbon in carbon steels. And for some of you, I'm going so slow, saying all the same. For some of you, I might be going at the speed of light. For those of you who think I'm going slow, please bear with me, because I want to bring everybody on board with the class. For those of you who think I'm going at the speed of light, please take a look at your introductory to material science books. And if you don't have any or you don't know where to go, I can make some suggestions. You don't need to relearn a whole course, but some basic concepts, like I mentioned, you need to know, because that's the way you understand what's happening during welding. All right, we talked about effect of temperature, and we talked about effects of carbon. And we talked how when we cool down, we could have different type of microstructures happening. What I didn't say before is that it doesn't happen instantaneous. If I say, okay, all of you iron atoms, rearrange from FCC to BCC, the atoms are gonna say, you know what, I need some time here. Sometimes the time is fast, sometimes the time is slow, but it matters. It's never zero. So what gives this time? What decides this time? And as I explained this to you, all of a sudden you're gonna make so much more sense about steel alloys and problems in welding. Austenite can take a whole lot of carbon. So I would like somebody to tell me through the chat, what is the maximum amount of carbon I can dissolve in austenite? How much carbon can I put in austenite? Anybody wants to type a number? Yes, thank you very much. 2.11, yes, 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 it's right here. I cannot put any more carbon than that in austenite, but 2% is a lot, right? Now you don't see this here, but in ferrite, the amount of ferrite I can put, I believe is 0.022%. Maybe I'm missing a zero there. Very, very little. Now, let's think together. If we're going from austenite, for example, at 0.2% carbon, it's a lot more than ferrite can take. So the austenite is happy. The austenite says, oh, I only have 0.2% carbon. I'm like 10 times less than what I can take, no problem. And then all of a sudden it gets into ferrite. And ferrite says 0.2% carbon, you're crazy? It's this is like 10 or 100 times more than I can take. And what happens then? Well, what happens is that the carbon needs to get out of the ferrite. That is what is called carbon partition. And that takes time. How does it happen? Typically, the limiting factor is the diffusion for the carbon to get out, right? We talked about diffusion bonding, right? This thing in which the carbon atoms are moving through the crystalline lattice, right? In this case, it has nothing to do with bonding, but everything to do with atoms migrating through the lattice. So that takes time. And when the perlite is being created, right? The carbon needs to get out of the austenite, so the austenite can turn into ferrite, and then that carbon needs to go into the cementite lamella. So right there, you can imagine, because there is this diffusion happening, if I have like a very coarse perlite, I have a long diffusion path, and it takes long to do. If I have a fine perlite, I have a short diffusion path, and that can happen faster. You start to see now why the metallurgists always answer things like, it depends. Because if you ask, okay, how long does it take for perlite to, austenite to decompose into perlite? They're always going to ask you to answer, it depends. And they will answer your question with another question is, okay, how coarse the perlite or how fine the perlite? But now you can start anticipating them, right? Right now, what matters is you get a sense that these coarse microstructures have a long diffusion path, and that therefore take long to form, and fine microstructures have a short diffusion path and therefore take short times to happen. So because we have diffusion, right? We talked about longer distances mean longer times, but also a transformation that involves diffusion. I'd like to hear your thoughts. Does it happen faster or slower if I'm at a hotter temperature, right? Does diffusion, right? Happen faster or slower at higher temperatures? Fast, of course, right? So now you start seeing, and we are only starting the conversation, but you start seeing a coarse microstructure takes long, fine microstructure takes short, but transformations at high temperature can happen fast, and transformations at low temperatures happen slowly. We start to put together some very, very important concepts that explain hydrogen cracking in the air, explain why we can mess up a weld with the wrong heat input. So if you bear with me, we go little by little. So let's discuss this effect of time. And I want to start discussing effect of time with paralytic steels, the ones that pretty much nobody welds, although we have a project in the lab right now welding these steels. These are the steels that you use for making railroad wheels or railroad tracks. And let's say we have that steel, and I want to propose an experiment. And the experiment is this. In this vertical line that represents the alloy, we are going to austenize, right? Or austenitize. I don't really know what I think the proper term is austenitize, but nobody says it like that. I'm going to austenize things at 800 degrees. So would be here, full austenite for 1 hour. So I give time for all the carbon to diffuse. Everything goes back to austenite, single phase. That is essentially, you have a lemonade, let's heat up the lemonade and can suck up so much more sugar, right? So that's what we do. And all the sugar is in solution in our lemonade, and all the carbon is in solution in our austenite. Then we're gonna cool very quickly, but we're not gonna cool down to room temperature. We're gonna cool down to different temperatures of my choice. The way you do this is using what is called a salt bath. If you quench in water, you essentially quench to room temperature. Certainly you don't quench above 100 degrees because there's no liquid water above 100 degrees. But if you use molten salt, you can do a quench that is more or less the same as a quench in water, but it's a pretty hot water, right? So we're gonna quench to 650 degrees, 540 degrees, and 350 degrees, right? Based on this diagram, right? Based on this diagram, 650 degrees is here, that corresponds to perlite, and 540 degrees is here, that corresponds to perlite. 350 degrees is here, all should correspond to perlite. So what's the point, right? Well, here's the point, is that thermodynamics that are used to build this diagram is part of the truth, but it's not the whole truth, because the time plays a role. That is what people call the kinetics, right? And so let's see what happens if I cool down and hold at that temperature. So cool quickly, I know that in the end result should be austenite. And in this graph here, to represent this, the effect of time, the horizontal axis is time and the vertical axis is percent transformed. So at the beginning, say at time 0, just time 0 is the moment I put it in my quench. At right the exact time I put it in my quench, because the atoms take some time to transform, which is not 0, I have 0% transformed, right? So this means 100% austenite at the very beginning, the instant in which I quench. And then I wait. And what do I see? Well, that if I wait long enough time, I'm going to have 100% perlite, that I know. And at intermediate times, we see, and people measure that, we have the machines to measure that in the lab, we see how we go from 0% transformation, the transformation gets faster and faster and faster and faster. And then as the transformation reaches completion, it goes lower and asymptotic towards the top, right? And so we can define somewhat arbitrarily, say, okay, let's say this start when I see that something has changed, or I can define it as 1% change. There's so many ways to define the start, and same with the finish. And people wouldn't agree, and they have big fights, and they write papers hating each other. And but let's all agree there is an arbitrary start that can be 1% or defined in a number of ways, and relatively arbitrary finish. People typically call the start when you whatever is measuring, you see a change, and the finish as with whatever you're using to measure it, you stop seeing that change. And that took some time. And we're gonna call this the start time, and we're gonna call this the finish time. Very important concepts. So let's see that transformation. If we go from 1 to, let's see, 1, 2, okay. 1, 2, 3, and 2, and 4. So if we cool down, right? And in the horizontal axis, we have time. In the vertical axis, we have the holding temperature. So in this graph I'm showing here, that is called the TTT diagram. When we quench into our salt bath, so remember, our salt bath is kind of red hot here. And I'm going to quench my steel into that salt bath, and at time 0, that is way to the left, nothing has transformed. We know that. And at some time, we have the start of transformation. Somewhat arbitrary definition, but most people would agree where it is, give or take. And this line here indicates as we move in time when the transformation starts. And then we keep transforming, and this other line here corresponds to the end of transformation, which is somewhat arbitrary, but most people would agree more or less where it is. Conveniently, the horizontal axis here is in log scale. So give or take 10%, you're never going to notice in the thickness of the line. So this is for one holding temperature. One holding temperature, we have now a start time for transformation, a finish time for transformation, at what temperature it is. And in this case, because it was a eutectoid steel, it transforms into coarse perlite, right? Because it's hot, so diffusion can move fast, and because diffusion moves fast, it can cover longer distances. The real science is way deeper than I'm making it sound like, but it's along the lines I'm telling you. If you're hotter, then like you can cover longer spaces because diffusion moves faster, and you end up with coarser microstructures. If now my holding temperature was at this 540 degrees, and I would have a different start temperature, and I would have a different finish temperature. Question to you. So how much faster is the start temperature if I'm at 540 degrees than if I'm at 650 degrees? How much faster do I see the transformation start? Twice as fast, 3 times as fast, 10 times as fast? Anybody who wants to venture an answer? How much faster does a transformation start? Yeah, ooh, 10 times, it's 10 times faster. So I have a vote for 15 times, kind of, right? This is 10 to, actually half a line here is a factor of 3. So this is 10 to 30 seconds to start at 650 degrees. And this is about 1 second to start at 540 degrees. You realize it's the same material. It's just I'm doing my heat treatment at different temperatures. And please, if you think this is too much metallurgy so far, please bear with me. I promise you, this explains welding. And for some of you, you don't need all this explanation. For some other of you, this might be the first time you see it. So and because now is at a lower temperature and diffusion is much slower, the transformation requires smaller spaces and we have finer microstructures. Just to make a mental note, in welding, we typically like small grains. So if we have transformations at high temperature, that will end up with coarse grains. When we have transformations at low temperatures, we end up with fine grains. Some of you might have heard about coarse grain zone and fine grain zone in the heat affected zone. Yeah, it's all this concept, right? Some of you might have heard about grain coarsening when we are at high temperatures. Yeah, it's all this type of same story. So I want to consider something else. In this graph, we have, if we transform from, we hold at a temperature, which we don't do this in welding, but this will help us understand. We hold this in this very contrived experiment at a temperature. We have start and finish temperature, start and finish time, start and finish time. Because you have this diagram, for every temperature you choose, I can give you a start and a finish temperature. If I'm above the transformation temperature, nothing's going to transform because I'm above the transformation. But what happens if I go and instead of quench my piece of steel in my molten salt, I quench it in water to room temperature, right? And this happens very fast. Well, what happens in that case is super interesting. If I quench it very fast, like the way you quench the swords in the movies, you make the sword and it's red hot and you're banging on it and you put it in water. What is happening? What's happening is amazing. The carbon doesn't want to be in the ferrite. We already discussed there's no room for carbon in the ferrite. The carbon wants to go to the austenite, but it needs time to get out of the ferrite and into the austenite because of diffusion. We already discussed that. And we said, okay, if we have shorter times or lower temperatures, we need shorter distances. But what if I cool so fast that there's no chance? In that case, the carbon has no escape. The carbon lives a very unhappy life inside the ferrite, and the ferrite lives a very unhappy life with the carbon inside. And it's all deformed. It goes from being a BCC, a body center cubic, to be a BCT, body center tetragonal. And now it's not so easy to deform because all the slip planes are like all wrong, and it becomes very hard. That's martensite. That's martensite, and it's very hard, and it's very brittle because you cannot deform it. And that's what happens when you cool down too fast. Low carbon steels is difficult to get martensite. High carbon steels or steels that have alloy, they can get martensite quite easy. Some steels, doesn't matter how you weld them, you're always going to end up with martensite. It's because they cool so fast that they reach this martensite transformation before they can start transforming. Isn't this interesting, right? And of course, the austenite is transforming into martensite, but everything's so twisted and so difficult that sometimes the same strains that are in this transformation, the same strains of like things getting all deformed internally, cause enough force to keep some of the austenite, what is called retained austenite, some of the austenite is going to be living at room temperature. Although, in theory, austenite should not exist at room temperature. But when we have all these very complex transformations, they induce stresses and strains that prevent it from transforming completely. So now you know, start time for a transformation, time to finish a transformation. You know how those times to start transforming depend on temperature. And you also know that if you cool too fast, you can not transform by diffusion, and you transform in a way that does not involve diffusion. That is martensite. In martensite, the carbon is essentially not moving. And now that I taught you, I can have a start of transformation and an end of transformation that ends up in perlite, and fine coarse perlite on top, fine perlite at the bottom. And then if we go crazy and quench to room temperature too fast, we have martensite. But what happens in welding most of the time is none of those. The structure that relates to welding the most would be reproduced in this experiment as follows. Let's quench in our salt bath, but let's quench to about 275 degrees. That it would be this height. So I quench very fast, but I don't reach the start of martensite. I do not transform martensite, but I hold it. Now, because I'm holding it, is taking long to transform, because at low temperatures, we have a very slow diffusion. It takes very long to start to transform, takes very long to finish transforming, right? Like, look, this is more than 100 seconds to start transforming. At this temperature, I could start transforming at 1 second. So depending on the temperature, I can transform in 1 second or in about 2 minutes. Same material. And to finish transforming, what it would be, these 10, 1000, this would be about an hour to finish transforming, while this other guy finished transforming in 10 seconds. What do you think? This is a fine microstructure or a coarse microstructure? Guesses. Fine or coarse? Fine, very fine microstructure. And in addition of being fine, is finer than perlite, also has some mixed aspects with some sort of a hybrid with martensite, because in addition of this small amount of diffusion to make these fine structures, we have some amount of displacement of the lattice, right? In the way austenite transforms to martensite is by a local displacement of atoms, in which the atoms move about like 1 atomic space, not a whole lot more than that. It's not a big deformation. And we see that in bainite. So bainite is an interesting thing that is kind of part martensite and part perlite. It's neither of those, but shares features of both, right? This bainite is quite ill-defined. Once upon a time, people were into something called the bainite wars, in which they were arguing about the mechanisms of transformation and what bainite actually was. Those wars are settled. However, you're going to see people talking about bainite as one thing, but some people talk about things like acicular ferrite or ferrite with second phase aligned, as if they were different things, but in reality, those are structures that share, and we're going to discuss those later. They are all have these bainitic traits, right? So we're going to be calling them bainitic microstructures, but not just bainite, because often when people say bainite, they refer to something very particular that looks like this. But in welding, things can look very differently, and still they are this mixture of a a little bit of diffusion for the transformation and a little bit of displacement too, like a hybrid of martensite and perlite. Okay, now what do we know now? We know start of the transformation, we know end of the transformation, we know the effect of time in the start and the end of the transformation. We know that at high temperatures, we're gonna get, coarse microstructures. We know that at low temperature, we're gonna get fine microstructures. We know that if we quench really quickly to room temperature, we're gonna reach martensite in most steels. Again, everything has a counterexample, but in most steels, if you quench to low temperatures, you're gonna reach martensite. And if you do holes at low temperatures, you're gonna find bainite. There is some sort of like a convenient hybrid. Very, very interesting. I would like to do a little test about how we're doing. I mentioned to you that if we are above these 727 degrees, in which thermodynamics tells us we have austenite, we will not transform, because that's what it should be. If I quench still in the austenite range, nothing is going to change. I have a question that I'd like to hear some thoughts. We all agree that at low temperatures, diffusion is slow and the transformation, therefore, is slow. We're fine on that. I would like to know your thoughts of why, if I'm at high temperatures, the diffusion is fast, my transformation is slow. I'd like to hear why, if diffusion is fast, my transformation, as you get to see here, at high temperatures, the transformation is slow. Thoughts? Ah, thank you. Okay, good. This is fantastic. Low driving force, that's the answer. Right on this line of equilibrium means there's no driving force. That means the atoms are just as happy being austenite. Right below the line means, you know, I don't really want to be austenite, but I don't feel so bad about it. When you're here, they really are far from being austenite, and they don't want to be austenite. They're all quick to change. But here, the driving force is so slow. Yeah, austenite, well, in both, below this line, austenite is unstable. So the comment of austenite is more stable actually should be phrased as austenite is less unstable, right? Because it's not stable. About the amount of carbon, no, the amount of carbon is always the same. And this is a very important concept now. I'm talking always about the same steel. Same thing. I'm just doing different things to the steel, and the steel is responding to it. Steel is alive. Steel is like a person. And if you treat it well, it's going to be your best friend, right? But you just have to know how to treat it. And but the amount of carbon is the same. We're not talking about two different steels. It's always the same thing in which we're doing different types of heat treatments. So let's talk now about an example with 0.4 carbon. And if you remember, just before we talk about start time and finish time for a eutectoid composition, in which it goes from austenite to perlite. Very easy. And then we also talked briefly before about a 0.2% carbon alloy in which there was primary ferrite, right? In this 0.4% carbon steel, we are in this regime. This would be relatively high carbon steel to weld, but I chose 0.4 because I have some data on it. And at this composition, as it cools down, we're going to go through the intercritical region. And as we go through the intercritical region, this indicates that thermodynamics says that at some point we should have primary ferrite, right? Because we're going through this ferrite and austenite dual phase field. So we're gonna do the same experiment as before. Now, if we close our eyes, we're in our shop, we have our furnace to heat things up for 800 to 800 degrees for 1 hour, what means I'm going to dissolve all the carbon, and the austenite is all one happy phase. This is like heating up your lemonade so it dissolves all the sugar, right? You don't want to drink it hot, but the sugar went in for sure because it's hot. And now what we're gonna do is the same example as experiment as before, quench very quickly in molten salts, not in water, because we don't want to reach room temperature. I want to quench to a temperature and hold. And let's see what happens. Much the same as before, but there are some subtleties that appear in welding that I want to discuss with you. The microstructure in equilibrium, in all cases, should be primary ferrite that came as we crossed this two-phase region, and then the austenite that comes, if you do the lever rule, when we are going down this line, just before the full transformation, we're gonna have some amount of ferrite at this composition and some amount of austenite at this composition. If the lever rule you don't remember very well, or you don't remember very well how to run or operate with phase diagrams, take a quick look. This is very basic. So we're gonna be using this concept. So primary ferrite and this austenite turns into pearlite. That's what we should expect. So let's see. This diagram on the right is the same TTT diagram we had discussed before. Transformation, time and transformation, time and temperature transformation diagram, TTT, time and temperature transformation diagram. So let's see, this is the composition of our steel, the blue line. And here we reach this line is called A3. A3 is when the austenite starts to decompose. And this at A3 is when the atoms might as well stay in austenite. They don't really care about leaving home. And what do we see? At this temperature, nothing is transforming. If I do a quench to this other temperature that is just above the line, just above the A1 line, the line at which no austenite could exist, just above that line, what do we see? We see that we would have transformed primary ferrite. These TTT diagrams all have different name conventions, so you have to know what to expect. This says A plus F. That means you have an austenite at the beginning that is like gasoline in your car, is driving the motion. This is the austenite, and the austenite started to transform here at this point. This is a start of transformation. And as time goes by, it's transforming. What is it transforming into? It's transforming into ferrite. It's just above this line. And is it going to finish transforming? Never, never, because there will be austenite always forever retained there. So look at this diagram. This is different than the one before. First precipitates primary ferrite and then keeps going. Let's go to this other line at 600 degrees. If we do our hold at 600 degrees, what are we going to see? Some amount of primary ferrite, and then of course we'll start transforming into pearlite, right? So at this temperature in which I should have ferrite and pearlite, what it says is I would have a relatively little amount of primary ferrite, and then the rest is pearlite. The amount of primary ferrite we're gonna see in this steel that is quenched in these conditions is smaller. The amount of primary ferrite is going to be smaller than, or can be smaller than what we see thermodynamically, because now we have some kinetic issues at play. All right, let's say we cool down now to, let's pick 450 degrees. 450 degrees, we quench and do the hold. And now this part, this is the start of the curve, and this is the end of the curve. A stands for austenite, F stands for ferrite, C starts for cementite. And here F plus C means ferrite and cementite and no more austenite. Ferrite plus cementite is the composition of perlite and is the composition of bainite, right? It's ferrite and cementite. So they are not telling you what, but I'm gonna tell you something. Is an approximate way of knowing if you're gonna have perlite or bainite is, you see the nose? Transformations above the nose tend to be perlitic. Transformations below the nose tend to be bainitic. And look at this, very funny, in this steel in particular, the end of transformation has two noses. One nose for the end of perlitic transformation, and another nose here for the end of bainitic transformation. And of course, if we quench down very fast, we would be crossing the martensite start temperature, and we would have all martensite. So what do we know now? We have talked about start and end temperatures, and now we have start and end temperature, but we have start of ferrite, start of primary ferrite, then start of bainite, in this case, start of perlite, and then end of transformation. It's a little bit more complex than before. It's the same thing, but we keep adding concepts and concepts. And still, please stay with me, because this introduction is essential for us to understand welding. So, okay, I had some images here, but the notes are uploaded, right? And we talked about the martensite. So what have we discussed so far? We have discussed the effect of temperature and the effect of carbon in our steel. We have also discussed how the effect of time and how when we start transforming and when we finish transforming depends on what temperature we're talking about. At high temperatures, we have low driving force, so we start and finish late. At low temperatures, we have huge driving forces, but diffusion is very slow. So we start and finish late. But there's some intermediate magic temperature at which diffusion and driving forces are kind of all in the sweet spot, and we can start and finish quickly. And this gives us different microstructures. At high temperatures, we have coarse microstructures because high temperature have high diffusivity is fast, and we can afford the long distances. At low temperatures, diffusivity is slow, and we cannot afford the long distances, and microstructures are fine. When we go crazy all the way, quenching down to low temperatures, then the carbon has no chance to diffuse out and is trapped and is unhappy, and it distorts what would be a ferrite lattice, that is a BCC, becomes a BCT, that is polycentric tetragonal. So instead of being a cube, now is kind of a prism, and it's very hard and brittle because it cannot deform. We saw all those things, and we saw also that there is an intermediate when we talk about holds below the nose that has some attributes of martensite, such as some diffusionless aspect, and some attributes similar to perlite, so some amount of diffusion. And these bainitic microstructures are very common in welding. And look at this. So far, we have been talking about only carbon, iron and carbon. I didn't talk about chromium and nickel and manganese and all those things. And guess what? It's always there. Indeed, I mentioned to you when we were talking about consumables, how manganese and silicon pick up oxygen from rust. But if I'm using a high manganese wire in a clean plate, the manganese is gonna stay inside the metal and can give us trouble, because alloying elements also change these start and finish times in our phase transformations. And changing the time combined with the how fast or cool we're cooling down, how fast or slow we're cooling down our weld, can end up in the wrong combination of hardness. So how do we discuss the effect of manganese in our steel, or other alloying elements for that matter? That is the concept of hardenability. So let me start with an important disclaimer. Hardenability does not say that a steel per se is harder than other steel. What it says is that it's easier to get harder by transformations. So a hardenable steel and a non-hardenable steel, if both are martensite, they have more or less the same hardness. Not exactly, we'll give you formulas for that. And if you cool down very slowly, it's gonna be more or less the same. The difference is that how fast do you need to cool to reach this martensite? Typically in welding, we don't want martensite. So we would like the steel to never have martensite. That means any cooling rate transforms. But very hardenable steels, what happens is they can transform martensite easily. How does this happen? Remember the start time and this end time for the transformation? If we make it very slow, the cooling time in welding can end up taking us into martensite, just because the transformation was so slow. So people design steels to be hardenable historically because heat treatments were difficult. And now what is good for a heat treatment typically is bad for welding. Okay, it's 3:20. And what I would like to do is to stop at this slide and pick up on hardenability again on Thursday. We're gonna have time, we're gonna have 3 lectures on metallurgy. And we're gonna meet again in 10 minutes. And Alejandro prepared some really cool slides with something that involves some concepts we're gonna be using later too. But with formulas for you to predict the hardness in a weld. Extremely powerful stuff. And Alejandro is going to go over concrete examples of that with you. And on quiz 2 next week, I will ask you to do a calculation along these lines. So we're gonna teach you these formulas, and I'm gonna suggest that you make an Excel spreadsheet. I'm going to suggest that you make a spreadsheet. Of course, I can give you a spreadsheet. It wouldn't be all too difficult. But because it's not too difficult, I would like you to do it. So you have to read the formulas in detail and think about them. And on Tuesday, please check to make sure that they work well. And on Tuesday, I'm going to ask you to put it to good use. All right. I'm going to stop here and meet with you in 10 minutes.